In part 5, we learned how to deform shapes with the vertex shader and use tessellation shaders to improve the fidelity of a wave shader effect. In part 6, we're going to learn all about lighting in shaders. It's a long one, and we're gonna cover a lot of ground, so strap in. So far, our objects look a bit flat, and that's because we're applying no lighting at all to them. Regardless of whether the object is in full view of the main light, or obscured by shadow, or if part of the mesh is facing away from the light, the object is fully lit. Today, we're going to change that. First, let's learn about some basic lighting techniques. Real lighting is extremely complicated, so we use approximation models to simulate light that's close enough to real light. One of the simplest of these models, called the Phong reflection model after its creator, splits up lighting into 3 different components. First, we have ambient lighting, which you can think of as background lighting. Even objects in total shadow appear slightly lit due to the way light indirectly bounces off objects onto other objects. So we can approximate it by adding a constant light level to everything in the scene. Next, we have diffuse lighting, which you can think of as an overall lighting level, which is dependent on the angle between the surface and the light's direction. If something is facing more directly towards the light source, it has a higher diffuse lighting, and vice versa. This kind of lighting doesn't depend on the angle that you view the object at, because it models a rough surface which reflects incoming light rays in all directions, which means that the amount of outgoing light is proportional to the incoming light. Finally, we have specular lighting, which causes the shiny highlight on objects. Specular highlights happen when an object's surface is sufficiently smooth enough to reflect a high proportion of the incoming light in the same direction. It's kind of conceptually the opposite of diffuse lighting in that respect, although surfaces usually have a bit of both. Because of this, specular lighting is dependent on the light direction, the surface facing direction, and the angle you are viewing the object at. Let's jump into writing the shader. I'm basing this code off the basic texturing shader from part 2, but I've renamed it basic lighting at the top of the shader lab code. In this shader, we will get the lighting information from the main light in the scene and apply the 3 kinds of lighting that I just mentioned to the object. To start off, let's add some properties. I only need 2 for this shader. The first should be the ambient lighting, which I will express using a color property for now. The ambient light should be fairly weak in most cases, so I'll use a default value of 0.2 in each of the RGB channels. We can tweak this later to be higher in brightly lit environments or lower in dark indoor places, and we could even use a color tint rather than a grey value like I've set here, but I digress. The second property should be a float called glossiness, which controls the overall shininess of the object, and therefore how prominent the specular highlights on the object will be. Remember to define both of these variables in the C buffer, using the float for and float types for the ambient lighting and the glossiness respectively. Since we are working with lighting, we can change the name of the main shader path. After all, this is no longer an unlit shader, is it? Let's set the light mode tag to universal forward, which is a tag that Unity understands to mean this is a URP shader which does lighting. We also need to import a file called lighting.hlsl from the URP shader library, as it contains all the functions related to accessing the lights. Then let's think about what sort of information we're going to need in the app data and V2F structs. As I mentioned, diffuse lighting is proportional to the angle between the surface direction and the light direction. Typically, we represent the surface direction using a normal vector, which points perpendicular to the surface at a given point on it. This is a direction, so it is represented as a unit vector, which is to say its magnitude is equal to 1, which is what you get when you normalize a vector. That's going to be important later, but for now, let's just include the normal vector inside app data. When we calculate lighting inside the fragment shader, we will need the normal vector in world space, so we can add that to the V2F strat. I'm also going to need the position in world space too, but we'll see why when we get to the fragment shader. And finally, I mentioned that the specular lighting is based in part on the angle between the viewer and the surface, so I'm also going to include the view direction vector, which points from the surface to the camera. Of course, now we'll need to calculate all these new vectors inside the vertex shader. The clip space position and the UVs work as usual, and we've seen the transform object to world normal function before, as we used it in part 4 for rendering depth information in the depth normals prepass, so let's use it here. You should also be familiar with the transform object to world function, which I'm going to use to get a world space position vector. The only new function here is called getWorldSpaceViewDir, which takes in the world space position as an input and gives us a world space view direction as a result. This vector actually isn't normalized, even though I want to use it to represent a direction. There's a similar function called getWorldSpaceNormalizedViewDir, but I won't bother using it here for reasons you'll see shortly. That's it for the vertex shader, so let's move on to the fragment shader. Currently, we are just sampling a texture and multiplying it by base color. We can leave this code alone for now. Above it, let's calculate some lighting. The very first thing I'll do, before I even get the light data, is set up some data that I'm going to be using inside this function. First, let's get the normal vector using the normalizeNormalPerPixel function. Actually, you might be wondering why we even use this function in the first place. Imagine this is one of the faces of the mesh, viewed side on, and here are the normal vectors at two of the vertices. Both are unit vectors. When we rasterize this face into pixels, Unity interpolates the normal vectors for the intermediate pixels between these vertex normals. The problem is, with linear interpolation, it's like drawing a straight line between the two endpoints, and then picking a point on the line. And if we're working with vectors, in most cases, all of these interpolated vectors will be shorter than the original unit vectors. Since the later fragment calculations rely on the normal vector being unit length, that's why we normalize. We could use HLSL's built-in normalize function for this, but normalizeNormalPerPixel includes a bit of safety to handle cases where a zero vector is input. Next, we need to do the same for the view direction. I don't think there's a library function for this specifically, so I'll just use the normalize function. Then I'm also going to get a shadow coordinate. I want to be able to read the light's shadow mapping data, and to do that, we need to supply a shadow coordinate to sample the shadow maps. Fortunately, Unity provides the transform world to shadow coord function, which accepts the world space position as input, so we don't need to think about this too much. Now we can access the main light in our scene using the getMainLight function, which optionally accepts the shadow coordinate as input. Usually the main light refers to the first directional light, which you are probably using to model the sunlight, just like the URP default scene template. We get the light in the form of a strut containing these values: direction, color, distance and shadow attenuation, and layer mask. I'll sidestep the layer mask for now. The direction and color should make sense, and then there are these attenuation factors. That's just a fancy way of saying that the light gets reduced if we are far away or in shadow, and they are values between 0 and 1. When one of these values is equal to 1, that means the light isn't being reduced at all. Either we're very close to the light or it's not obscured by another object. For a directional light, the distance attenuation is always 1, but you can keep that in mind for point lights, whose attenuation will fall over distance. With that in mind, I'm going to create a variable to store the main light's overall color, which is as easy as multiplying its color and its two attenuation values together. Next, let's create a variable for the ambient lighting. For now, it's a bit redundant since we're just using the property we set up, but later I'll swap this for something different. Then we can calculate the amount of diffuse lighting. As I mentioned, diffuse lighting is related to the angle between the surface normal vector and the light direction. When both vectors point in the same direction, we get maximum light, and when they are perpendicular, we get no light at all, with a smooth fall-off between these extremes. We can express this as a function where the diffuse lighting is equal to the cosine of the angle between the vectors. Now, I'll also display the formula for the dot product between two vectors. It also has a cosine of the angle in there, multiplied by both the lengths of the input vectors. Now, this is why we needed to use unit vectors, since these both evaluate to 1 and we can simplify this expression. For any two unit vectors, their dot product is equal to the cosine of the angle between them, which is equal to the amount of diffuse lighting. That makes it very easy to express in HLSL, since there is a built-in dot function. This function actually goes below 0 though. When both vectors are opposite, the result is -1. So I'll use saturates to clamp the output to a 0 to 1 range, and then I'll multiply by the light color. Next, let's handle the specular lighting. This is equal to the dot product of the view vector with the reflection of the light vector across the normal vector. You can kind of see it in the diagram that specular lighting comes about from lots of light reflecting off the object, all in the same direction and directly into your eye. First, we need to calculate that reflected vector, which we do with HLSL's reflect function. The first parameter is the vector being reflected, and the function expects this to point towards the surface. Currently, it is pointing away from the surface towards the light itself, so we can negate the vector to flip its direction. The second parameter is the normal vector, which we are reflecting the first vector in. Then we can calculate the amount of specular lighting by taking the dot product between the reflected light vector and the view vector. Once again, I'll saturate it to bound it from 0 to 1. This will eventually give us a bright white highlight on the surface, but I want to use the glossiness property to control its size. I will do that by raising the dot product result to the power of glossiness. Since we're always getting a result between 0 and 1, this means the highlight gets smaller the glossier the surface is, which is close enough to how shininess works in the real world. I'll also multiply by the main light color here. I'm personally unhappy with the way that glossiness has diminishing returns if you use it like this. Once you go high enough, you have to really crank up the glossiness to see any appreciable difference in the size of the highlight. So I'm actually going to use 2 to the power of glossiness here instead. Now, the change in the size of the highlight is a little more uniform as you change the glossiness here in the inspector. Now we get to the final part of the fragment shader, where we combine the lighting with the original unlit color we were previously using. I'm going to quickly rewrite these lines slightly so that this first line gives us the base color in its entirety. Then I will calculate the final output color for the shader by adding the ambient and diffuse lighting together and multiplying them by the base color. Then to that, I will add the specular lighting. By adding the specular lighting at the end and not multiplying it by the base color, the specular highlight ends up being far more visible than it otherwise would be, which is what I want. The last thing to do in the fragment shader is to output that final color, although I also want to make sure that I output the alpha component of the base color. If we hop into the scene view, we can use this shader on a sphere mesh and see it reacts to the light in real time. If we move the camera around, then the diffuse lighting doesn't move around the object, but the specular highlight will follow the position of the camera. And if we rotate the directional lights, then the shaded region of the diffuse lighting will change position too. The one thing that doesn't seem to work is the shadows from the other objects, and there's a good reason for that. Welcome to what I like to call keyword soup. Keywords are sort of like switches that we can toggle on our shaders. Later, we will add our own custom keywords, but Unity defines quite a few, and we can add them to shaders to enable or disable certain features. For example, inside the URP shader library, here are some snippets of the code that Unity uses under the hood to get the shadow attenuation values. You can see here that it uses a preprocessor directive to check if this thing called main_light_calculate_shadows is defined, and if not, then the function just returns 1, which means there's never any shadow. Unity only ever retrieves real shadow values if it's defined. In turn, we define this calculate shadows thing only if one of these other things is defined, either main light shadows cascade, or main light shadows screen. These three things are keywords, and our shader does not define any of them currently. Now, finding out which Unity keywords you're meant to add to enable specific features in your shaders can be very annoying, as they are not terribly well documented anywhere. So one trick I like to use is to literally just open up one of URP's basic shaders and peek at what sort of keywords they define. If you scroll down in your project view to the packages section, you can find the URP included shaders and just open one, such as lit. You won't be able to modify them, but we can at least see how they're written. Inside the universal forward pass, we can see some keyword soup. We group keywords together on each line, and only one member of a group can be active at once. This one here looks like it has those three keywords we just saw in the shadow attenuation function, so let's yoink them. We say hash pragma, then multi-compile, which means Unity is going to compile a separate shader variant under the hood for every possible combination of these keywords being enabled or disabled. Then we put this little underscore, which represents a sort of null keyword, which is set when none of the following keywords are set, and then we name all the keywords in the group. These three keywords represent three different ways that Unity can render shadows. The first is for regular shadow mapping. The second includes shadow cascades, where you change shadow quality based on the distance from the camera, and the third is for screen space shadow mapping. I don't really care which sort of shadows are being used, but we do need all of these to cover our bases and ensure shadows always work, no matter which shadow setting someone is using. I also like the look of this one here, called Shadows Soft. This one is for blending the edges of shadows slightly for a softer look. It uses multi-compile fragment, which just means that this keyword is only available in the fragment shader. Now I've copied both of these keyword groups into my own shader, just below the include files, and I can go back to the scene view and see shadows working properly on my sphere. Next, I want to change the way that ambient light works in this shader. Let's disable the main directional light for a second. Nice to see our shader doesn't just immediately break, and it's just showing the ambient light we set up. If we compare it with the URP lit shader, you'll notice a very subtle lighting difference between them. The lit shader is a bit darker on the bottom and has a slightly bluish tint on top, and that's because it gets ambient light from the environment, namely the skybox. We can do the same, and it's actually quite simple to implement. Inside the shader, we are currently setting the ambient light using the property we created, but instead, we can grab the environmental ambient light using a function called sample_sh instead, which stands for spherical harmonics. This function takes in the world space normal vector as input. Under the hood, this function is a bit complicated, but thankfully, this is all we need to do to use it. If we go back to the scene view, our sphere will show the same behavior as the URP lit shader. This is down to preference, of course. If you think it's more useful to just use the property we set up before, then you can keep that instead. I'm actually going to leave the property here even though I'm not using it now, and I'll revisit it in a future tutorial. The ambient light isn't the only difference between the URP lit and our shader, however. You'll see this very slight, soft glow around the outer edge of this sphere. This is called Fresnel lighting, spelled like this and named after this French guy, and it's kind of a special case of specular lighting that arises when you view something at a very shallow angle. That's why it appears on the outer edge of a sphere. At all these parts, the angle between the view direction and the normal vector is at its highest. I'd like to incorporate Fresnel lighting in our shader. I'll add two properties for the Fresnel lighting, one called Fresnel power, which will be arranged between 1 and 20. We will use this value to control how far the Fresnel lighting extends across the mesh surface. The larger this value, the smaller and thinner the Fresnel highlight will be. Then I'll add a Fresnel strength value between 0 and 1, which is a multiplier for the Fresnel lighting. Without this, I think it's a bit too strong, so it's nice to be able to turn it off. Remember to add both of these properties in the C buffer too. Let's go directly to the fragment shader and create a variable for the Fresnel lighting. At its core, Fresnel lighting depends on the angle between the normal and view vectors. so we can throw both of those in a dot product and saturate its result. However, unlike the other kinds of lighting, this is meant to get stronger as the angle increases, so I will subtract this value from 1. This gives us a base Fresnel lighting amount. I will then raise this value to the Fresnel power property that we added before, which lets us control the size of the Fresnel highlight, and then I'll multiply the result by Fresnel strength to give us a final Fresnel lighting amount. I can just add Fresnel lighting to the final color calculation we previously did alongside the specular lighting, and we're done. And if you've been taking this shot every time I say Fresnel, I'm so sorry. In the scene view, we can tweak the power and strength values until we've got something that looks pretty similar to the URP lit shader. I like to add Fresnel lighting to my shaders because it helps to make objects stand out a bit in front of other parts of your scene. So far, we are relying on the mesh geometry to give us all the normal vector information. However, for detailed objects, it's not feasible to model all these small crevices and shapes on the surface, so it's common to use normal maps to do that. A normal map is a texture which encodes the normal vector at each point on the surface in a special format, so we can read such a texture using the same set of UVs we would use for a base texture, and then unpack the color data into a new normal vector which we can use instead. We'll need a couple of new properties for this. First, a normal texture, which will use the same 2D type as the base texture, but the default value will be bump, which I mentioned was one of the options back in part 2. This makes the entire texture look bluish, and it's equivalent to a totally flat normal map. The other property will be normal strength, which controls how deeply the normal map changes the surface normal directions, which I'll make a range from 0 to 2. The URP lit shader doesn't bound this value, but I just think it looks a bit silly when you make it very high. Remember to add the normal strength to the C buffer, and we'll add the normal texture just below the base texture alongside its sampler. Now let's think about what the normal texture represents. At each point on the surface, the color values in the texture encode a direction. Unity provides a function called unpackNormal, which converts those colors into a tangent space normal. This means that the vectors are relative to the surface facing direction. Before we can use it in our calculations, we need to convert it from tangent space to world space. Doing the conversion involves taking the tangent space normal and multiplying its x component by the world space tangent vector, which points along the tangent space x-axis. Then we take the y component and multiply it by the world space bitangent vector, which points along the tangent space y-axis. And finally, we take the z component and multiply by the world space normal vector, which points along the tangent space z-axis. We add those three results together and then normalize, and we've got ourselves a new normal vector in world space. Reading the tangent vector from the mesh data is easy enough. We can just include an entry for the object space tangent vector inside the app data struct, making sure that it's a float 4, and the semantic is called tangent. Although the tangent vector itself is 3-dimensional, just like the normal vector, this fourth component will be useful later. I'll also be passing this data to the fragment shader, so let's also define a world space tangent vector in the v2f strat, with the next available text coord semantic, which is text coord 4. In the vertex shader, let's convert our tangent vector from object to world space using the transform object to world dir function. That only works for the first 3 components of the vector, but I'll just preserve the original 4th value and pass it to the fragment shader. In the fragment shader, let's sample the normal texture using the syntax that we are familiar with. This is still just color data, so to decode that data and convert it to a normal vector, we can pass it into the unpackNormal scale function, which also takes the normal strength as an input. That gives us a tangent space normal vector, as I mentioned. And finally, let's do the conversion from tangent space to world space. We have the normal and tangent vectors, but we also need the bitangent vector. It's perpendicular to the other two, so we can just use the cross product between them to obtain the bitangent. We also need to multiply by the tangent vector w component, which determines the direction that the bitangent should face, and also multiply by a variable called unity underscore world transform params dot w, which helps ensure that the bitangent faces the correct way when your object uses a negative scale in any of its axes. Then, now that we have the bitangent vector, we can do those multiplications I mentioned earlier, which gives us a new world space normal vector that we can use to override the old one. Let's head back into the scene view and attach a normal map to our material. When we do, the lighting will change on the object as we expected. If we combine this with a corresponding base texture, then we can see how a normal map really makes the lighting feel a lot more realistic. By the way, if you want some homework, try modifying the depth normals path to use this new normal map. I'll give you a hint. You'll need to add a C buffer to that path, but it needs to be the same as the one you use in the main path or Unity welcome plane. Check out the GitHub repository for my completed version. We've done a lot of work on this shader so far, but we're only considering one light, the main directional light. Our shader will be far more effective if it could react to other real-time lights in the scene, such as point and spotlights. I'm going to clone the basic lighting shader and name the copy additional lighting. Remember to rename it at the top of the shader file. In this shader, we will loop through each additional light and do the same lighting calculations we used for the main light. And that means we need to dive into more keyword soup. This first one here will let us use light cookies, which are mask textures that we can apply to a light to block part of it out. They're useful for giving lights a bit more texture, like if you wanted to represent a dirty light bulb. These next two enable us to get information from any additional lights in the scene, and their shadow information. And this last one enables us to use the forward plus renderer. I haven't really talked about the different rendering paths in URP yet, and I won't go into tons of detail now, but the short version is that with forward rendering, we loop over every light in the scene for all pixels, so it gets expensive pretty quickly as you add more lights. And forward plus rendering tries to slow down that rise by doing a sort of pre-pass, so you only read lights which are actually reaching the pixel that you are drawing. This keyword lets us take advantage of both rendering paths. Hey, post-production Dan here. In Unity 6.1 and onwards, Unity renamed this to Cluster Light Loop instead. Kind of annoying, but just bear in mind that you should use that instead. I want to keep this tutorial working in 6.0, so I'll use forward plus, but Unity will warn you to change it in version 6.1 and beyond. You can change between paths using the universal renderer data asset near the top. You'll notice that there's also a deferred renderer option, which I will discuss in a future tutorial. There's a great technical article which goes over many of the differences, which I'll link in the description. Now that we have prepared our keyword soup, let's move on to the app data and V2 abstracts. Later, when we access the additional lights, to get accurate shadow information, we will need to supply a shadow mask, and to do that, we need a second set of UVs. Apart from the main UVs, which we have already seen in the UV0 channel, Unity uses the other UV channels for other purposes. UV1 is used to sample bait light maps, which are textures containing pre-calculated lighting values for static objects, and UV2 is used for dynamic light maps, where moving objects or lights can update their shadow data each frame. The shadow mask uses these dynamic light map UVs. Unity automatically sets the light map UVs onto your meshes, so we don't need to do anything special to set them up. But we do need to read from them, so we can define a dynamic light map UV in the app data struct, and use the text coord 2 semantic to get the correct channel. The number is important because when we read mesh data, we want to pull from a specific text coord channel. We will also need to pass these UVs from the vertex shader to the fragment shader, but now it's just arbitrary data. So we will use the next available text coord channel, which is text coord 5. In the vertex shader, we need to pass those UVs to the fragment shader, but we'll need to apply light map tiling and scaling to them first. We did the same thing with our main UVs, but with those, we relied on the transform text macro, which pulled the scaling and translation data from a texture. Instead, for the dynamic light map UVs, Unity gives us a variable with the scaling and translation information, and we need to apply it manually. That's actually pretty simple to do. We can multiply by unity underscore dynamic lightmap st.xy, and then add the ZW components. That's actually what transform text does under the hood. Now, in the fragment shader, we can use that lightmap UV to set up a shadow mask using the sample underscore shadow mask function. This will allow us to get the correct shadowing data from our additional lights. Speaking of which, let's add some codes to read from those between the code for the main light and the part where we sample the base texture. Let's wrap this section of the code in a preprocessor directive by saying #ifDef, short for ifDefined, and then the name of one of our keywords, in this case additional lights, and then ending the block with #endIf. We're telling Unity to compile whatever is inside this bit of the code only if there are additional lights in the scene. In here, we will add the light loop using a macro, but we'll need some data for it. Let's initialize an instance of a struct called inputData, which is defined somewhere in the URP shader library. This struct has many fields, which I'll explore in the next part, but for now, we only need to set the world space position, which we already have access to, and a normalized screen space UV. There's a handy getNormalizedScreenSpaceUV function for this, which accepts the clip space position as input. Unity uses these values to find the lights from the forward plus prepass if you're using it. Next, let's set up that loop. Unity gives us a function to get the number of lights called getAdditionalLightsCount, and then we can set up the loop using the lightLoopBegin macro, which accepts the light count as a parameter. Under the hood, this is using the input data to set up a for loop which iterates through each light, giving us a light index value for each iteration. We can use the getAdditionalLight function and pass in that light index, plus the world space position and the shadow mask, to finally get data about each additional light. Using the light, we can do diffuse and specular lighting calculations just like those we did for the main light, but this time, we will use the plus equals operator to add both kinds of lighting to the main light's values. We do this because lighting is additive. The total diffuse lighting on a surface being affected by two lights is equal to the diffuse lighting from one light plus the diffuse lighting from the other light. Crucially, we don't need to add the ambient or Fresnel lighting a second time, as they both act as forms of indirect lighting. That's all we need to do in the shader to add additional lighting, so let's go back to the scene view and add a couple of point lights. If we move them around our mesh, then we'll see the lighting update in real time and react nicely to any normal map that we have on the object, including an additional specular highlight for each light acting on the object. Shadows also work nicely as long as you have them enabled on the light itself. If you move a mesh using our basic lighting or additional lighting shaders between the light and another object though, you'll notice that neither of them cast shadows right now. There's one last thing I want to add to the additional lighting shader, and you can add it to any other shader too if you want. Shadow casting is handled by an additional pass, just like the depth only and depth normal passes. Essentially, the scene is rendered from the perspective of each light, drawing the depth of each object into the shadow map texture. We don't need to worry about setting each render up or anything. We just need to write the correct information in our shader. This happens before the main shader pass, so when it needs shadow information, we'll know if the thing being drawn is in shadow if it's further from the light than the depth value drawn in the shadow map. Let's add a new pass. I'll slot it between our main pass and the depth passes, and I'll set its light mode tag to Shadowcaster, which is the designated name for this type of pass in URP. I'll ensure that ZWrite is on, and since only the depth is relevant for this pass, I can also say color mask 0 to bypass writing color entirely. Next, we have the HLSL program block. My vertex and fragment functions will be named ShadowPassVert and ShadowPassFrag respectively, and I'll import 3 files from the URP shader library: core, lighting, and shadows.hlsl. We need a single keyword in this pass called casting punctual light shadow, which is used by Unity to use different functions later in the shader, depending on whether we are drawing shadows for a directional light or other kinds of light. Then we need two HLSL variables, light direction and light position, both of which are float-free types. We don't need to include these inside a C buffer because they are not shader properties that we added. Instead, they are passed directly to the shader via URP's internal code. Next, we have the app data and V2F structs. These are fairly simple. The app data struct just needs the object space position and normal vectors, and the V2F struct only needs the clip space position. Now I'll move on to the vertex shader function. This just needs to output the clip space position, which we'll handle using a function called getShadowPositionHClip, which will accept the object space position and normal as inputs. Now, this function isn't included in the URP shader library. I'm stealing it directly from the URP lit shader, with a couple of minor modifications. I'll just define it above the vertex shader. When writing shadow information, we can't just do transform object HClip to the position, since this can cause a shadowing artifact called shadow acne, where a surface shadows itself. Instead, the surface is moved very slightly inwards along its own surface normal to avoid the problem. So first, we can get the world space position and normal vectors using two familiar functions, transform object to world for the position, and transform object to world normal for the normal vector. We need these because the light position and light direction vectors are defined in world space. Next, we can use the casting punctual light shadow keyword to choose how we get the light direction vector. For non-directional lights, we subtract the vertex position from the light position and normalize the result. For directional lights, we just grab the light direction variable directly. Finally, we can set up the clip space position output using the transform world to HClip function. We are going to pass in another function called apply shadow bias, which takes in the world space position, normal, and light direction, and it's going to return a new position which has been moved slightly along the normal as I described. Finally, let's make sure that the shadows are clamped to a reasonable range using a helper function called apply shadow clamping, and then we can return the clip space position. The only thing left to do inside this pass is to add the fragment shader function. It has the same structure as most of our fragment shaders, and then inside it, we don't really care what it returns, since only the depth values are important, and those are handled automatically by Unity outside of the fragment shader, so let's just return 0 and be done with it. In the scene view, if we cover a light with an object which uses our custom additional lighting shader, then we'll see that it now produces shadows perfectly. The nice thing is that this pass can be copied into our existing shaders and it will do what we want. The only thing to remember, and this applies to the depth only and depth normal passes too, is that if you want to physically move any vertices, such as with the wave shader that we created in part 5, or discard any fragments, which happens in an alpha cutout shader, like the one from part 3, you ought to also modify these passes to do the same vertex movements or fragment clipping. That's one advantage of Shader Graph, I think. It handles generating all these passes for you, which is really nice. I think we did a lot in this tutorial, but lighting is a huge topic and there's always more to learn. With that in mind, in part 7, we will learn about physically based rendering, a way of shading objects based on the way light operates in the real world, which also uses parameters which describe the physical properties of the surface. Until next time, have fun making shaders.